Okay, so once again, in section 12.2, you computed some double integrals, but that was over rectangular regions in the xy plane where all the limits were constants. Now, I'm going to make a comment right here about that. If your limits are not all constants, you can't switch the order of integration just like without worrying about the limits. Okay, and section 12.2, we're going to talk about double integrals over general regions. Okay, so like they have here in figure 1 and figure 2, general regions. So, without getting too complicated here, let me just show you some type 1 regions. So in figure 5 here, you have what are called type 1 regions. So you can see that the regions in the xy plane are general regions D, and they're bounded above and below by these functions g1 of x and g2 of x. Okay, those are called type 1 regions. Now, you can also have what are called type 2 regions. Type 2 regions are regions where you're bounded on the left and the right by functions of y. So here in this figure, you have figure 5. You're bounded above and below by functions of x. But you can also have a situation where you have type 2 regions. And type 2 regions, you're bounded on the left and the right by functions of y. So you see, by allowing functions of variables to be form your boundaries, you allow yourself a wider range of problems that you can do. The integrals, it's sort of natural then to think what the integrals would be, what the double integrals would be. So like, for instance, if you have a type 1 region, okay, type 1 region, where your region in the xy plane is bounded above and below by bounded above by g2 of x and bounded below by g1 of x, this would be what your double integral is. Okay, it's that simple. And then d of x goes from the limits a to b. So in other words, you're used to, in section 12.2, when you had dy dx, you had limits going from a to b and c to d. Well, now, if you let your y limits be functions of varying functions of x, you replace c and d, which are constant functions, you replace them with functions g1 of x and g2 of x. Okay, and then the integration works like you did before in section 12.2. So, like for example, here they want you in example 1 to evaluate this double integral where the region D is a region bounded by parabolas. Okay, y equals 2x squared and y equals 1 plus x squared. So in order to do that, in order to find that region, you need 4 limits. You got 2 limits. You got the parabola. You got a parabola below, which is y in figure 8, y equals 2x squared, and then you have a parabola above, which is y equals 1 plus x squared. And that's fine. But then what about the x limits? Well, the x limits would be where the 2 parabolas intersect. That's how you find your x limits. And the parabolas intersect at -1, 2 and 1, 2 at those coordinates. So therefore, to compute the double integral, okay, to compute the double integral, this would be how you compute it. So your top function, your top parabola, again, if we go back to the picture, I want to make sure I'm not moving too quickly here. Here's the picture, figure 8. We want to find the volume underneath the surface x plus 2y over this region, okay? And the region D. So you're bounded above and below by functions 1 plus x squared and 2x squared, okay? And maybe I can have it both show nicely here. Hold on. Yeah, that'll work a little better. And then you're bounded, the x limits are going to go from -1 to 1. Are there any questions on figure 8 and the double integral that you see there, that you see right there? All right. Well, so this is clearly a type 1 region, and we have the double integral there. And, you know, we just, you know, we get the antiderivative of x plus 2y with respect to y, which is xy plus y squared. And then we substitute in our limits, which are functions. And the rest is computational. The rest is computational. Okay. Are there any questions on this example? All right. So, you know, I'm trying to make it, it's really just, I mean, if you're comfortable with section 12.2, 12.3 you should also be able to become comfortable with. It's just with 12.3 you have to you know, find your limits. Unless they're given to you, you have to draw a picture of your functions and find your limits. Sometimes a region, by the way, can be both type 1 and type 2. Okay, so here they want you to find the volume of the solid that lies under the paraboloid, under this paraboloid, z equals x squared plus y squared, and above the region bounded by this line, y equals 2x, and the parabola, y equals x squared. Okay, so in this problem, well, all you need to do is draw the region. The points of intersection are going to be 0, 0, and 2, 4. Not hard to find. You could do that algebraically very easily. And it could be treated as a type 1 or a type 2 region. Okay, so if you're a type 1 region, you see in figure 9 that blue vertical, that like blue line segment with the arrow on it. That shows that you're treating it like a type 1 region. And if you treat it like a type 1 region, your top limit is 2x, your bottom limit is x squared. And so this would be then how you compute that double integral. And the limits go from 0 to 2, the x limits. Okay, that's if you're treating it like a type 1 region. On the other hand, you can treat the region as a type 2 region. See here? Here you have the same region D, but the little line segment, the blue line segment in figure 10 goes from a function on the left to a function on the right. Now the function on the left was originally y equals 2x, but you can write that as x equals a half y. And then the function on the right was y equals x squared, but you can write that as x equals the square root of y. See, you're writing x as functions of y, okay, to get these sideways functions. And then when you integrate this, when you do the double integral, you're going to be integrating with respect to x first. And the left and right limits are half y and the square root of y. Okay. And so there's how you compute that double integral. And sometimes, class, it's much easier to do an integral with respect, well, you know, the region, you can treat it, I mean, sometimes it's easier to treat the region as a type 1 region. Sometimes it's easier to treat the region as a type 2 region. It really depends. It really depends. Okay. And like, for instance, they have, well, are there any questions on this example too? All right, well, if you're good with that, then let's move forward here. Let's move forward. Okay, so here in example 3, okay, they want you to evaluate this double integral where D is a region bounded by a line and a sideways paraboloid. The line is y equals x minus 1, and I'm sorry, it's a parabola, and the parabola is y squared equals 2x plus 6. So what they do is they draw a picture in figure 12 of the region. And in figure 12, well, so in this example 3, the parabola y squared equals 2x plus 6. If you take the square root of both sides, you're going to get y equals plus or minus the square root of 2x plus 6. And so in figure 12a, they've graphed, they're treating the region D as a type 1 region, which means you need a function on the top, a boundary function on top, and a boundary function below. And so you're going from y equals negative square root of 2x plus 6 on the bottom to y equals square root of 2x plus 6 on the top. But the thing is, what happens in figure 12a when you treat region D as a type 1 region? Well, the function on the bottom changes from the parabola to the line, to that line segment, y equals x minus 1. And so, in other words, for this problem here, if you're gonna compute the double integral and treat region D as a type 1 region, you're gonna need 2 double integrals to handle that. You're gonna need two double integrals. You're gonna need the sum of 2 double integrals. In other words, this is what you would have to do if you were to treat this region as a type 1 region, if you wanted to compute that double integral. So you see, it's quite a bit of work to do. You can do it, and I've actually done it. I worked it out on my own, but it's this region D, in this example 3, you're going to see it's much easier to treat the region D as a type 2 region instead of a type 1 region. If we go back to the figure, here, look at figure 12b. If you treat the region D as a type 2 region, okay, then the entire left side of the region is bounded by the parabola x equals y squared over 2 minus 3. And how we got that was if you take y squared equals 2x plus 6 and write it as, rewrite it in terms of x, you'll get x equals y squared over 2 minus 3. And then the line on the right, the line there, y equals x minus 1, that can be written as x equals y plus 1. So if you treat region D as a type 2 region, you're going to have a much simpler integral. You're only going to need one. You're only going to need one. Okay, you're only going to need one. To compute the double integral. So that's the thing. Well, first of all, are there any questions on this example 3? All right. Well, so I mean, this is really just gives you an idea of what's going on here in this section. And I think what I'd like to do is give you some. If there are no questions, I'll stop the recording for section 12.3.